Swayam Prabha. Digital India. Educated India.
Hello everyone, today we will continue our discussion of the general model of transport, and this model was essentially given by Landauer in 1950s, and then it was later developed by Professor Datta and later on Mark Lundstrom. So, in this formalism of mesoscopic devices, small devices, few tens of nanometers of channel, the devices that have that kind of a channel, we started our discussion from a two terminal device, and this third terminal at the moment we are not considering. So, please ignore the third terminal, the gate terminal at the moment, and so generally the model is, or which is actually quite close to the reality, that the contacts are large and the channel is small. And in that case, the electrons in the contacts are characterized by their Fermi functions and Fermi level EF1 or EFS, and Fermi level here is EF2 or EFD. So, what we discussed in the previous class is that the source contact tries to bring the channel in equilibrium with itself, which means that it tries to fill all the electronic states up to its Fermi function, its Fermi level. So, it will try to sort of make sure that n1 prime electrons are there in the channel. When the channel is in equilibrium with the source contact, n1 prime electrons will be there in the channel. Similarly, on the drain side, when the channel is in equilibrium with the drain contact, n2 prime electrons will be there in the channel. In steady state, when both the contacts are connected, the channel is not in equilibrium with any of the contacts, and it is the steady state. The flow is, there is a flow of electrons, and the flow becomes very quickly the flow becomes constant, and that is known as the steady state. In steady state, the number of electrons in the channel is n prime, and if we consider the energy range from E to E plus dE, n1 prime E is the number of electrons in the channel in the energy range E to E plus dE, n2 prime E is the number of electrons in the channel from energy range E to E plus dE, and n prime E is the number of electrons in the channel in the energy range E to E plus dE. With these quantities, we could write the rate equations essentially. So, the rate at which electrons are hopping from source into the channel is essentially will be given by n1 prime E minus n prime E divided by tau 1 E. In some cases, even the characteristics time is a function of energy, which means that in different energy levels in the channel, the time that the electron takes to go from the contact to the other end of the channel is a function of energy. Okay. But for simplicity, we assume that both the contacts are symmetric and tau 1 is equal to tau 2 is equal to tau, and it is independent of energy. Similarly, the rate at which electrons will be jumping from the drain contact into the channel will be given by n2 prime E minus n prime E divided by tau 2 E. in steady state the net flow is constant. So, the rate at which electrons are jumping from the source into the channel will be equal to the rate at which electrons are jumping from the channel to the drain, or the net rate of electrons coming to the channel is 0, which, so this can be written as F1 plus F2 is equal to 0, or F1 is equal to minus F2. So, this is the steady state situation in the device. Okay. In addition to this, what we know is that N1 prime is equal to N1 prime E is equal to density of states in the channel times the Fermi function of the channel, number of allowed electronic states in the channel, times the probability that a certain state is occupied by the electron according to the Fermi function of source contact, times the energy gap. Similarly, N2 prime E is density of states of the channel times the Fermi function of drain contact times energy range dE. This is what we know. In steady state, we see that F1 plus F2 is equal to 0. So, if we put these quantities, so F1 plus F2 is equal to 0, and if we put F1 is essentially N1 prime E minus N prime E divided by tau 1. Similarly, F2 is N2 prime E minus N prime E divided by tau 2, and that is equal to 0. So, if we assume tau 1 is equal to tau 2 is equal to tau, in that case N1 prime E minus N prime E plus N2 prime E minus N prime E will be equal to 0. So, essentially this N prime E, which is the steady state concentration of electrons, number of electrons in the channel in steady state, will be given by 1 by 2 N1 prime E plus N2 prime E. Okay. So, if we here put down the expressions for N1 prime E and N2 prime E, the number of electrons in the channel in steady state in the energy range E to E plus dE will be F1 E dE plus 1 by 2 dE F2 E times dE. Okay. So, this is the expanded form of the expression. That essentially takes us to this expression N prime E, the number of electrons in steady state in the channel in the energy range E to dE plus dE will be equal to dE times F1 E plus F2 E by 2 times dE. Okay. So, this is the expression for the number of electrons in the energy range E to E plus dE in the steady state in the channel. Okay. And if you look at the expression, this expression is I would say intuitively justified as well, because as we also saw in the previous class that the source contact is trying to make sure that that electrons are filled in the channel up to EF1, or it is trying to fill the channel with Fermi function F1. The drain contact is trying to fill the channel with Fermi function F2. So, let me rewrite it here. N prime E is dE F1E plus F2E divided by 2 times dE. So, now when both the contacts are there, in that case the channel is filled with a Fermi function which is the average of the two Fermi functions. So, let us say this becomes the Fermi function of the channel. In the steady state. Okay. So, the total number of electrons in the channel will be now. So, the total number of electrons in the channel will be the integration of the number of electrons in the energy range over all possible energy ranges. This will essentially be integration over all allowed energy ranges dE times F1 E plus F2 E by 2 times dE. Okay. So, as I said, this also makes sense intuitively as well, because one is trying to fill the channel with Fermi function F1 source, the drain is trying to fill the channel with Fermi function F2, and both of them together will fill the channel with Fermi function F1 plus F2 by 2. Okay. So, we have obtained the total number of electrons in the channel in steady state from this simple analysis of the rate equations in the device, two terminal device. Now, so this was one of the first objective, to find out what will be the steady state population of electrons in the channel. So, before the contacts are connected to the channel, the electronic population would have been somewhat different. When the channels are connected, this will be the steady state electronic population in the channel. Okay. Now, let us see and more importantly, we also want to find out what will be the current in this device in steady state, and that is what we will see now. In steady state, the rate at which electrons are going from source to channel is F1. The rate at which electrons are going from source to channel is essentially F1, and the rate at which electrons are going from channel to drain will be minus F2, as we have seen earlier. So, this is F1, that will be F2, and in steady state we saw that F1 plus F2 is equal to 0 or F1 is equal to minus F2. So, the current in the steady state current in the steady state will be steady state current will be Q times F1, because F1 is the rate or number of electrons per unit time that is getting from source across the channel, or minus Q F2, that will be the current in the steady state. Now, let us see what it turns out to be. So, I will be q times F1, and F1, if you recall, is N1 prime E minus N prime E divided by tau. It can equivalently be written as, from minus q times F2, it can equivalently be written as N2 prime E minus N prime E divided by tau. As I have made it clear that tau 1 is equal to tau 2 is equal to tau is assumed. So, this can be written as q n prime E minus n 2 prime E divided by tau. So, this will be the steady state current in the system. Okay. So, if we put down, we have now the expression for n 1 prime E and n prime E as well from our earlier from the derivation on the previous page. N 1 prime E is essentially d E times F 1 E into the energy range. Similarly, the n prime E, the steady state electronic population in the channel will be d E times F 1 E plus F 2 E by 2 times d E. Okay. Please remember that we need to write I as a function of E as well, because this is the number of electrons in the energy range from E to E plus dE. So, this IE will be the contribution or the current contribution of the electrons in the energy range from E to E plus dE. Okay. So, if we take this part and put the values from here, IE will be q by tau n 1 prime E essentially is dE times F 1 E into dE minus n prime E is dE into F 1 E plus F 2 E by 2 times dE. Okay. So, this will be the contribution in total current from the electrons in the energy range E to E plus dE. On further simplifying this expression, we can take dE outside. In the bracket, we will be left with F 1 E minus F 1 E plus F 2 E by 2 into dE. Okay. So, finally, the current due to electrons in energy range from E to E plus dE can be written as, if we simplify this further, it can be written as q by 2 tau dE. This 2 will come out F 1 E, or let me not write it here, let me not write the 2 here, it can be written as F 1 E minus F 2 E by 2 times dE. this is the current due to electrons in the energy range from E to E plus dE. As you can see, and if you compare this to this expression here, this is the electronic population in steady state in the device. This is the current contribution due to electrons in the energy range from E to E plus D in the device. Okay. If you see here in the expression for the steady state electronic population, we have F1 E plus F2 E by 2. In the current expression, we have F1 E minus F2 E by 2. So, that is the most striking difference in these two expressions, apart from a constant, apart from another term as well, which is this. This tau can be, as we know that there is a relation between gamma and tau, and it is gamma is h bar by tau, or tau can be written as h bar by gamma. So, this I e can be written as q by h bar gamma d e into f 1 e minus f 2 e d e. So, just another way of writing this thing, and the total current in the device will be essentially the integration of this expression over all possible energy values. So, this will be the expression for the total current. Intuitively speaking, the steady state electronic concentration depends on the average of the Fermi functions f 1 e plus f 2 e by 2, and the steady state current depends on the difference of the Fermi function, and that is also what we discussed intuitively as well. So, what we discussed was that if we plot the band structure or the energy level scheme of the device, this is EFS, EFD, these are various states in between. The more the difference between EFS and EFD or EF1 and EF2, more will be the current, more will be the difference in F1 and F2. So, the more is the difference between the two Fermi functions, the Fermi function of two contacts, more will be the current in the device. However, that is not significant. This difference in the Fermi function is not important for the electronic population. For electronic population, the average is more important. Okay, the average of the two Fermi functions is more important. So, that's an interesting observation, and that's an important point to keep in mind, which is also intuitively expected. Okay. So, this is what we have. So, we have ultimately obtained the expression for the current and the expression for the steady state electronic population in the device, when the device is a two terminal device is connected to the two contacts, and this is what we were trying to see right from the beginning. I would say that these equations are among the most important equations in mesoscopic device analysis and even nanoscale devices. These equations are extremely important starting points. Okay. So, in order to find out current in a device, we need to know the density of states of the channel, we need to know the Fermi functions of the contacts, we need to know this gamma parameter, which is essentially related to the transit time. It also, in other words, captures the interaction of the contacts with the channel. So, we need to know the Fermi functions in the contacts, we need to know the density of states, we need to know the interaction between the contacts and the channel. There is there is another approximation that we need to keep in mind, which I did not explicitly mentioned earlier. In these devices, it is assumed that the contacts are reflectionless. What it means is that the electron that travels through the channel is completely absorbed by the corresponding contact to which it strikes. Similarly, if the electron travels from here to here, they do not reflect the electrons back. What it essentially means is that this junction between the contacts and the channel is as perfect as it can be, which is practically not the case always. There are some imperfections, there are some dangling bonds or some states, trap states or at the interface. So, those impurities or those imperfections are not taken into account in this analysis. We are considering that this junction is perfect between the contact and the channel, and the electrons are traveling such that electrons are not reflected back by the contacts. Okay. So, with these equations we will now see how we obtain a new idea, a new notion in the device analysis, which is generally known as the modes in the channel. Okay. So, so this is the expression for the current. Okay. So, what we obtained was we derived an expression that the current is, the total current is Q by H bar, okay, into gamma into dE into F1E minus F2E by 2 times dE. This was the total current expression that we derived. It can be simplified further if we write H bar equals H by 2 pi. In that case, this expression becomes 2 Q by H, and this is a constant. So, it can come out of the integral gamma, and it can also be a function of energy times pi times dE times F1 minus F2 by 2, and these two F1 and F2 are also functions of energy. We are not explicitly writing it, but it should be kept in mind, and this is essentially the expression for the current, which is what is written here. So, here as you can see, there are, so we need to properly understand this equation. In fact, I would suggest you to sort of remember this equation, and you do not need to explicitly remember this final expression. If you do the derivation yourself, you will understand it clearly and you will not forget it. So, so this equation has a constant term which involves fundamental constants. One is the charge of the electron, second is the Planck constant. In addition to that, it involves the difference in Fermi functions F1 minus F2, which is expected. The more the difference, more the current. So, the difference is necessary for current to flow through the device. So, if there is no difference between the Fermi functions of the source and the drain, the current will be 0. However, that is not the case with the steady state electronic population. Okay. If we bring this 2 here and sort of remove the 2 from here, we know that this is a fundamental constant, we know this is what is required, but we do not know what this quantity is. This gamma E, we know separately, gamma E is the energy broadening, dE is the density of states, pi is a constant again, 2 is a number, dE is the energy range. But this quantity is an interesting quantity that we need to analyze. So, please think about this, and we will discuss more about this in the coming class, what this quantity is. This gives, let me give you a hint, this is known as the modes in the channel or the conduction pathways in the channel. Just to give an analogy, it is more the number of modes, more will be conduction pathways in the channel, and more current will flow through the device. And please keep in mind that this is different from the allowed energy states. So, modes is not exactly equal to the allowed energy states, which is given by the density of states. It is different notion than that. It involves density of states and the broadening of the states. Okay. So, we will start discussing this new concept known as the modes in the next class. So, please do these are simple derivations with the approximations clearly in mind. You can do these derivations very simply. I would recommend all of you to do these derivations on your own, and then you would remember these expressions as well. Okay. Thank you for your attention. See you in the next class.